Hi everyone, I am Jay from Virginia Tech. I'm glad to present our work on learning compact representations of neural networks using discriminative masking. A primary motivation of our work is to prune over-parameterized neural networks. Over-parameterization is widely prevalent in modern deep learning applications. It acts as a hindrance to their adoption in resource-constrained environments. It can also make them susceptible to overfitting, thus motivating their pruning. Pruning methods can be broadly categorized as unstructured versus structured pruning. In unstructured pruning, individual parameters are pruned, leading to an overall sparse subnetwork. On the other hand, in structured pruning, entire substructures of the network such as neurons or filters are pruned, leading to sparsity in the future representation of this network. In this paper, we focus on the problem of structured pruning. This is because while unstructured pruning leads to sparse networks with smaller memory footprint, they do not necessarily lead to speed improvements, as the number of feature computations during testing remain the same. On the other hand, in structured pruning, entire substructures of the network are pruned out, leading to smaller number of features to be computed during testing. This results in faster inference speed, along with smaller model size. A common strategy for structure pruning is by applying the concept of masking. Here, for every layer that needs to be pruned, we take the atomar product of the neuron activations with a learnable mask to generate scaled outputs. By setting smaller mask values to 0, we can prune out entire neurons, thus perform structure pruning. In the figure, we show an example of applying mask values to a layer with 4 neurons. Here, if we want to prune 50% of the neurons at this layer, we can prune 2 neurons with the lowest mask values 0.3 and 0.2 by setting their mask values to 0. Now that we are familiar with the concept of using learnable masks for pruning, let us discuss the process of training the learnable masks for a general neural network without hidden layers. Here, the activations of the ith layer are denoted as psi of I, while the learnable mask for that layer is denoted as g of I. The entire network can then be represented as a composite function of the layers. The learning objective of structure pruning by masking then involves minimizing 2 terms. The first term is the task-specific loss, while the second term is the L0-based sparsity regularization term that ensures that the learnable mask at every layer g of I have fewer non-zero values. We are specifically interested in enforcing L0 sparsity over the mask values. However, directly minimizing L0 sparsity is an NP-hard problem. Hence, most methods tend to minimize some approximation of L0, for example, the L1 norm, and then perform some corrections to achieve fewer non-zero mask values. This results in a variety of procedures for structural network pruning. Out of all the procedures used for structured pruning, the most common procedure is to apply 3-stage pruning, where the first stage involves training the neural network. In the second stage, the network is pruned by minimizing some approximation of L0 sparsity, and then removing non-zero weights by performing some correction. A drawback of this step is that, since correction methods do not provide a principal solution to minimizing L0 sparsity, the training accuracy can significantly drop after pruning stage due to the removal of non-zero weights, leading to training instability, especially for aggressive pruning ratios. Finally, to recover the lost accuracy, the pruned model is fine-tuned over the training set in the third stage. Note that fine-tuning adds additional computational costs to the overall pruning procedure. Also, there are multiple strategies for fine-tuning, and selecting the best strategy for a problem is non-trivial. Another procedure for structured pruning is to repeat the training, pruning, and fine-tuning stages multiple times in a multi-pass scheme. This can help in resolving the instabilities of a single-pass schemes. However, multi-pass procedures are significantly more expensive than single-pass methods. In contrast to existing methods for structured pruning, we present a single-shot pruning procedure where the pruning is performed jointly with the training by directly minimizing L0 sparsity. Since our procedure provides a systematic approach to directly minimize the L0 sparsity of the learnable masks, it does not require any fine-tuning and hence shows much faster training. The basic intuition behind our approach is to use an ordering among neurons to perform direct L0 minimization of mask values. To understand this intuition, let us assume that we are given the ideal ordering of neurons in a layer, representing their importance of being pruned. Based on this ordering, we can prune neurons incrementally by masking out neurons with a lower order before going to neurons with a higher order. For example, given a layer with 4 neurons as shown in the figure, we can first sort the neurons according to their order, and then prune the neurons based on their order to achieve different levels of L0 sparsity. Note that this concept of pruning neurons based on their order is related to magnitude-based pruning methods. For example, network slimming and ChipNet, where neurons with smaller mask magnitudes are considered less important and hence are pruned first. Now that we understand the concept of neuron ordering, the next question to ask is, how can we get the neuron orders? Note that finding the ideal ordering of the neurons that reflects their importance while pruning is a non-trivial task. However, we can leverage the intrinsic symmetry of neuron weights generated by commonly used neural network initialization schemes to arrive at a very simple ordering scheme. In particular, since the weights of every neuron are independent and identically distributed before the training process has begun, all the neurons are equally important for pruning. Hence, any arbitrary ordering of neurons in the layer can be used to perform pruning. For simplicity, we use the index of a neuron at a layer as its neuron order in our pruning procedure. We empirically demonstrate in our paper that random permutations of neuron orders have no effect on pruning quality. We now present our proposed approach of discriminative masking, or DAM. The basic idea of DAM is to use a gate function to obtain mask values for neurons at every layer. Specifically, for the jth neuron at a layer I, we obtain its mask values gij using the gate function shown in the figure, which monotonically increases with the neuron order μij. At epoch 0, the gate function is shown as a blue curve in the figure, which outputs non-zero mask values for all the neurons, indicating that no neurons are pruned. As the training process continues and the neuron weights are updated, we horizontally shift the gate function such that, at epoch t, the mask values are non-zero only for a few neurons with higher orders as shown in the right curve. In this way, we can discriminatively mask neurons based on their order such that, at the end of the training, only a few neurons have non-zero mask values. To implement our gates function, we use a very simple parametric form, which is a composition of ReLU and a 10H, and is a function of the neuron order μij. Having ReLU ensures that our gates function produces mask values that are exactly equal to 0, thereby strictly enforcing L0 sparsity. 10H allows the gates function to be monotonic with respect to μij. Alpha ij is the scale parameter which controls the stiffness of the gate function. We keep alpha constant in our experiments. Beta I is the only learnable parameter of our gates function, which we refer to as the offset parameter. Reducing the value of beta I horizontally shifts or offsets the gate function, thus controlling the percentage of neurons pruned with a lower order. In this animation, we can see that reducing beta I shifts the gate function to the right and hence increases the percentage of neurons pruned at a layer I. Hence, by minimizing the betas of all layers in the learning objective, we can gradually prune the neurons at all layers along with minimizing task-specific loss. In fact, minimizing the betas at every layer directly leads to minimizing the L0 sparsity of the learnable masks, as theoretically demonstrated in our paper. We next show some results to demonstrate the power of DAM for structured pruning. We compare our results with two state-of-the-art structure pruning baselines. The first one is network slimming, which is a widely used baseline method for structure pruning. The second one is ChipNet, which was recently proposed this year and achieves state-of-the-art performance on benchmark datasets. In the figure above, we compare the performance of DAM with baseline methods on CIFAR benchmark datasets, where the x-axis shows the parameter remaining, or pruning ratios, while the y-axis shows the test accuracy. We can see that DAM significantly outperforms network slimming and achieves similar test accuracy as ChipNet across all pruning ratios, in spite of being a single-shot pruning algorithm. Additionally, we compared the time required for training and pruning. We can see that DAM is significantly faster than ChipNet since it does not require additional pruning or fine-tuning steps. We also analyzed the loss curves for each of the baselines to compare the stability of each of these methods during training. For DAM, we observed that the training loss decreases steadily and lead to a steady convergence. ChipNet also has a stable training stage, since it is identical to train a vanilla vision model. However, the fine-tuning stage of the ChipNet shows a sharp increase in the training loss for the first few epochs. Finally, for network slimming, both the training and fine-tuning dynamics appears to be highly unstable, and it leads to large fluctuations in the training loss. Another key contribution of our work is that we present a novel perspective of dimensionality reduction through the lens of network pruning. As shown in the figure, network pruning can be thought as simply adding a learnable mask after every layer such that the entire network is pruned and we end up with a smaller model. On the contrary, dimensionality reduction or representation learning can be viewed as just applying a learnable mask at a bottleneck layer, for which we aim to obtain a compact representation. To evaluate the effectiveness of DAM on dimensionality reduction problems, we synthetically generated three problems. In Figure A, we check if DAM is able to recover the bottleneck dimension of synthetic datasets generated using linear kernels of rank R, where R varies from 5 to 20. We can see that DAM can indeed recover the correct bottleneck dimension for each value of R. We also provide theoretical results to prove this behavior in our main paper. In Figures B and C, we can see similar trends for a polynomial kernel and a nonlinear neural network-based kernel. We also evaluated DAM on the problem of recommendation systems. Here, we used IGMC, which is a state-of-the-art method for this problem. We applied a DAM layer after the encoder layer of IGMC to reduce its bottleneck dimension. We can see that DAM provides a significant reduction in the bottleneck dimensions, along with slightly lower errors, demonstrating that learning compact representations can even boost generalization performance. We have obtained similar results on graph representation learning problems. See our paper for more details. Finally, we evaluated DAM using simple autoencoders on the problem of dimensionality reduction for the MNIST dataset. We compared the effectiveness of DAM with an ablation of our approach that minimizes the L1 norm. We also varied the trade-off parameter lambda to compare the sparsity of the learned representations. Figure A and B show that DAM is able to achieve lower reconstruction error, as well as higher F1 scores over the same bottleneck dimensions than the L1-based method. In Figure C, we can see that L1-based method has a saturating effect at larger lambda values, since the weights come close to zero but require some thresholding to be pruned. In contrast, DAM shows a linear descending trend of the bottleneck dimensions as lambda increases. In summary, we propose discriminative masking, which performs remarkably well over various applications of network pruning and representation learning, showing the versatility of our approach. DAM achieves state-of-the-art performance for structure pruning. Our approach is single-stage, does not require fine-tuning, does not suffer from training instabilities, and is also significantly faster than its counterparts. We theoretically show that the learning objective of DAM directly minimizes L0 sparsity. Our approach is also easy to implement and it can be applied to any layer of a neural network architecture. The simplicity and effectiveness of DAN provides unique insights into the problem of learning compact representations and its relationship with preferential treatment of neurons for pruning and refining, which opens novel avenues for systematic research in this area. In the end, we would like to thank our advisor Dr. Anuj for the great support for this work. Thank you for listening.